Now, I've just finished drilling this hole. With a standard twist drill, you can expect that this hole is within about 2/1000ths of an inch of the nominal diameter of the drill. The hole is also not terribly round. For many applications, this is good enough. For some applications, in particular when you're installing shafts or bushings or dowel pins, you'll want a more accurate hole. To do that, you often use a reamer. And this tool will consistently produce a hole that's within 2/10,000ths of an inch of the nominal diameter of the tool. To start with, you drill a hole with a twist drill slightly undersized from the size of the reamer. It's important to get a smooth finish with a reamer. To drive the reamer through the hole at a constant, slow speed. Going too fast produces spirals in the surface of the hole. So now we have a hole that is within 2/10,000ths of an inch of the nominal diameter of the reamer. A boring head is used for making very accurate holes. See here the adjustment dial is marked off in thousandths of an inch, and then there's also a vernier that allows you to make adjustments to a 10,000th of an inch. These adjustments are made by loosening screw on the side of the boring head and then turning the adjustment dial. This dial is attached to a screw which drives the body of the boring head back and forth in a dovetail way. You can see here. You set the position that you want. Lock the dovetail way down. Bring the tool down and contact the part. Making sure to take a very light cut. Boring tools are typically relatively long and thin, so they're not very stiff. So you take a large cut, although the tool is capable of removing a considerable amount of metal, you'll have a large amount of deflection in the tool as it's making the cut so that the hole you produce will not be the desired size. Spin the tool, making sure you don't contact any of the parts. Bring the knee up slowly by hand until the tool contacts the part, just to make sure that you are taking the depth of cut that you're intending to. Back the tool off and then engage the power feed. There are two different ways to do this. On machines that are equipped with a power feed on the knee, it's most desirable to use that power feed. Boring can also be done with a quill, but the knee can be fed more slowly, producing a smoother, more accurate hole. So I'll start by setting the power feed to 0. Engage the power feed. When I'm near the desired depth of the hole, stop the power feed, and feed the last few thousandths of an inch by hand. It's a good idea now to stop the machine before withdrawing the tool from the hole. Problem you may have if you're running the tool as you're removing it from the hole is that these chips can get bound up on the back side of the cutting tool and damage the surface of the hole that you just made. You can see here, if you look very closely at the hole, that this tool has produced a hole with a very, very good surface finish, and this hole has a diameter that is round to within the precision of the bearings in the quill. In this particular case, that means within about 50 millionths of an inch. Now we have a very accurate, very round hole, but we don't know what size it is, because this tool is not capable of absolute position adjustments. Now that I have a very accurate hole, measure to see what size it is. And the hole is now at 0.390. Now if I want to make this hole a little larger, say 0.400, what I would do is look at the reading on the boring head. In this case, it is 24 thousandths, and then I would increment that 24 thousandths to 34 thousandths to move the cutting tool out on the radius and increase the size of the hole. This tool is only capable of an accuracy of about 1,000th of an inch, whereas the boring head has the capability of producing holes to within about 2/10,000ths of an inch. So to take advantage of that precision, we can use a different type of measuring tool to measure these holes. We can use what's called a plug gauge. Here's a standard set of plug gauges. This set is made in 1,000th increments. They are also available in much finer increments. Look for the gauge nearest the size measured with the caliper, which is 0.390. And it doesn't fit. It's very close to fitting, but not quite. So it'll come down 1,000th of an inch. The 0.3890 plug gauge is a very tight fit in this hole, so we know, given that the tolerance of the plug gauge is plus or minus 1/10,000th of an inch, that this hole is 0.3890, probably minus 0 plus 2/10,000ths of an inch. Now we know much more accurately than we did with the calipers the true diameter of the hole. Now we can proceed to enlarge the hole to the final diameter. Boring tools come in a number of different sizes. See, this boring tool, aside from being much larger than the one I've been using, has all the same features. It has an adjustment dial, it's a lock, and it has several positions in which to insert a tool. In fact, it's possible with some boring heads to insert a tool in the boring head from the side. And this will allow you, in the case of this large boring head, to bore a hole that's 10 or 12 inches in diameter. In most shops, the most common operation performed on a milling machine is not surprisingly milling. The most common tool used for milling is an end mill. I have a variety of end mills here. Starting here, got a 1/16 inch end mill. This is at the smallest common size you use on a machine of this type. Here have a 4-flute 3/4 inch end mill, which is about the largest common size of end mill you typically use. Here is an end mill. It's called a ball end mill. You can see the end of the mill is ground in a ball shape to allow you to cut grooves with semicircular bottoms. Now, to use an end mill, just like most other tools, bring the end mill into contact with the workpiece, back the workpiece away from the end mill a few thousandths of an inch, move the end mill off the part, and if possible, rotate the tool to make sure that the end mill isn't going to run into anything unexpectedly. The depth of cut that you can take with an end mill varies with the size of the end mill as well as with the hardness or toughness of the material you're cutting. With all materials, eventually, as the cut you make gets deeper and deeper, you get to a point where the cutting forces are large enough to actually deflect the end mill. So as you feed the end mill through the part, the end mill tends to wobble. So the feature that you're machining will not have straight sides. To avoid this problem, you should make cuts that are shallow enough, keep the cutting forces down so that the tool does not deflect. You can look these numbers up in a book or, more often, experiment. Take a few passes, see what kind of cut the tool is producing. If you're having trouble, if the tool is moving around too much, take a lighter pass. With aluminum, can typically, the standard end mill, make a cut that is approximately as deep as the end mill is wide. This is a 1/2 inch end mill. It'll take a cut that's a 1/2 inch deep. You can see if you look closely at this back surface, the surface is reasonably smooth and flat. If I were to take a cut much deeper than this, however, you would see indentations in that surface due to the deflection of the end mill. It's a good idea when taking a cut that's this deep to have at least a few drops of cutting fluid place. Did not use any this time so you could see more clearly the cut as it was being made. Now, if you want to make a groove in a part that's, say, 1/2 inch wide, you do not use a 1/2 inch end mill. End mills are typically made only to nominal dimensions, so they're machined to within 1 or 2 thousandths of an inch of the diameter marked on the tool. To make an accurate groove in a part, you want to use an end mill that is the next size smaller, removing most of the material in rough passes like this. We'll remove another 1/2 inch pass. This time using some coolant. Now I'm going to offset the tool slightly. By taking a very light cut in this pass, I produce a very flat surface with a good surface finish. Now, I've not yet machined this part to the final dimension. What I will do now is measure the position of this side of the slot relative to the side of the part. Now I continue making passes on this side of the slot until the slot dimension has been achieved. Then start machining the other side of the slot, this time measuring the slot width and bringing the width of the slot out to the desired dimension. A shoulder or step can be machined to a part by bringing the end mill down, setting it at a point slightly short of the final depth of the feature. What I'm doing on this pass is called climb milling. In this pass, I'm doing conventional milling. It's very important to be aware of the difference between these two types of milling. In conventional milling, with a standard right-hand tool that is rotating clockwise, the part is being fed against the motion of the tool, like this. In climb milling, just the opposite is happening, where the part is being fed along with the direction of rotation of the tool. And the problem arises due to the presence of backlash in the table feed. During climb milling, it's possible you're taking a large cut to produce cutting forces that are large enough to drive the table, the vise, and the part the distance of that backlash. The result is that the next tooth of the cutter sees a very, very large piece of material, producing very high forces, often enough to break the cutter. And because the operator is typically standing right in front of the machine, very dangerous situation can arise with the cutter breaking and often flying out towards the operator. So be very careful when you're using climb milling. Climb milling will leave a much better surface finish, so it's a good milling process to use for finishing cuts. But for roughing cuts, in general, you should always use conventional milling. I'm making a pass now using climb milling and taking a large enough cut so that it will be very close to breaking the end mill. Now you can hear the part being pushed back and forth. If I'd taken a larger cut or been using a larger end mill, I would have probably broken the end mill. Cleaning a milling machine is a very important part of the use of a milling machine. If the machine is not kept clean, there's a risk of damaging parts due to chips, bits of dust interfering with the mechanism. When you're cleaning a machine, you should never use air. It's very tempting to use air and get the job done very quickly, but you risk blowing chips into machined parts of the ways, of the screws, and possibly damaging those parts. The proper way to clean a machine is with a brush or with a vacuum. Before you clean anywhere near the spindle, remove the cutting tool. Surprisingly, only a small percentage of the accidents in a machine shop happen while the machines are running. Most of the accidents happen when you're bringing parts to the machine or when you're cleaning the machine.